Right, so in this chapter, we're going to be looking at moments, and this is going to be in your year 2 applied book. And so first things first, what is a moment? Well, the definition or the equation for working out moments is force times perpendicular distance to the pivot. Now, a pivot is a point, something like here, where the rod or like a plank can rotate about. So that's what we call a pivot. So the force and the distance, perpendicular distance between the pivot and the force is going to be your moment. And in letter form, capital M is F times D. Now the units, or forces units is newtons, distance units of distance is meters, so the units are going to be Newton meters like so. So let's look at an example here. So let's say we got this plank here and we've got one force, there's 10 newtons force here at the end of the plank. And A, the pivot is in the middle. So to work at the moment, I would say moment about A, and I'm going to draw this like curved arrow like this. This just tells me that the moment going clockwise is going to be the positive, because moment is actually a vector form, so we need to tell us or the direction of which is going to be acting. Right, so taking moments clockwise about the pivot A, well, the force is 10, and the distance between the pivot and the 10 newtons, because A is a midpoint, is 5, so 10 times 5, which would give me 50 Newton meters. And because it's acting this way, it's going to make it rotate in this direction, right? But state that it's going to be a clockwise direction, like so. Right, let's add in another force. Let's say add another force here. This is going to be a 5 Newton force, and this distance is going to be 2 meters. Okay, and so let's work at the moments. So same thing, I'm going to do moments about A clockwise. So first things first, put the 10 thing here, right? So 10 times 5 is still remains. Right, now we have a second force where the force is 5 and the distance is from the pivot is this 2 meters, so times by 2. Now, important thing to note is this 5 newtons is pushing down, right? So it's going to make it rotate in an anti-clockwise moment or anti-clockwise direction. So for this particular case, we have to actually say 5 times 2 is going to be a negative value like this, because we said earlier that positive going clockwise is positive. And then therefore I have two different moments which I can sum up. So it's going to be 50 minus 10. So this is going to be 40 Newton meters clockwise. Like so. So if you have more than two forces, then make sure you've worked on moments individually, make sure you get the right signs, and then you add them up at the end. Okay, let's look at this example here. So you can see here that the force 10 newtons is still at the edge, a distance of 5 meters from the pivot A, but it's now acting at an angle of 30 degrees, so it's no longer directly downwards. And importantly, from the definition above, we said it's force times perpendicular distance to the pivot. So what does that mean? Well, if the force 10 newtons is acting downwards, and I have to just extend this force like here, the line of the force, the distance has to be perpendicular to the force, meaning that the distance I actually need to find is this distance here. I'm going to label it x, because this is now perpendicular to the force. So it's not going to be this 5 meters here, it's going to be this distance x. So if I was to do moments about A again, it will be 10 times this distance x, which we need to find. Right, so in this case, it's a bit more difficult, right, to try and find this x. So what I would recommend is changing up the definition of the moments. So remember, moments is it's perpendicular distance to the pivot times the force. What I would suggest you do is say it's perpendicular force times the distance. So change the perpendicular to going from the distance to the force. So what I mean by that is, well, if you can see here, this distance 5 meters, I'm going to leave it as 5. And rather than changing up the 5 meters, I'm going to change up the force's distance to make it perpendicular. So you can see here 10 newtons is at an angle. So what I can do now is just find this particular component of that 10 newtons force. Because you can see here, if I was to find the green force, then now the distance and the force would be perpendicular to each other. And finding the perpendicular component of this force is much more easier than finding the perpendicular distance of the distance. So how do I do that? Well, if I was to expand this out a bit larger, there's 10 newtons is here. We're trying to find this force here, and if I draw a right angle triangle here, because this is 30 degrees, this one will be 60 degrees like this. So this component here would just be 10 cos 60, like so. So now if I was to do moments by A, the force now will be 10 cos 60, and then I'll be multiplying by the distance of 5, so this is going to be 50 cos 60 Newton meters in a clockwise direction. Okay, so it's much easier to change the forces to make it perpendicular rather than changing the distance, because it doesn't really matter in the calculation. Let's try this one here. So we have more than two forces, or more than one force. We've got two forces, and they're acting at different angles. So within the moments, the pivot is at P, so moments about P, clockwise as positive. You can set anti-clockwise as positive, it's up to you, but generally I just set clockwise as positive. So let's look at each individual one first. Let's go to this 5 newtons first. So the distance and the pivot, or the distance and the force, are perpendicular to each other, as you can see here. So I don't have to change it up. I can just simply do 5 times 2. And as you can see, 5 newtons is going to make it rotate in this direction here, right? Which is a clockwise direction. So this is going to be a positive value like this. Second force. Now you can see the 6 newtons and this distance we're given is this 3 meters here. And they are no longer perpendicular to each other. They're at a certain angle, right? So what I'm going to try and do is I'm going to find the perpendicular force component. So i.e. I want to find this force here. Okay, I'm going to change it up to find this force here. Right, so we're given that this angle is 30 degrees. A way of changing up, well, I can say it's going to be equal to this force. I can split up like here, right? So this force here is the same thing as this force here. I'm going to call it xx, so the same forces. So this is 30 degrees, meaning this is also 30 degrees. To find the x, is going to be now 6 sine 30. So it's going to be 6 sine 30 degrees. Now times the distance of 3. And as you can see here, this is now going to make it rotate in an anti-clockwise motion. So this is now going to be negative, and make this equal to 0, and then you can find the answer. Right, so when we look at further questions, what you're going to be told in the question is that a certain like Planck or a question is in equilibrium. And we know that the equilibrium is when the resultant force is equal to 0. Okay, so the sum of all the forces is equal to 0. But now we've been introduced to moments, we also have to consider the resultant moment, and that also has to be equal to 0. Okay, so whenever we're given the term equilibrium, it just means that resultant force and resultant moment are equal to 0. So we have a uniform plank AB, has length 5 meters and mass 15 kilograms. The plank is held in equilibrium horizontally by 2 supports A and C as shown, and we're given some lengths. Find the reaction at plank A. So first things first, we need to sketch it. I would always recommend you guys sketching this when we're dealing with moments. We have A and C. Now A and C are supports, so whenever there are supports, these are known as pivots also. There's always going to be a reaction force going vertically upwards from these pivots or supports. And I'm going to label them RA and RC because they have different values. Another assumption we need to know is a uniform plank. If they say it's a uniform, it means the mass of the plank has a mass, but the mass is now acting at the middle. Okay, so if the plank is 5 meters in length here, this is 5 meters as they told in the question, the mass, which is 15 kilograms, is acting in the middle roughly here. And because we're dealing with forces, mass is not a force, it's going to be 15g, where 15g is the weight, which is also a force. So now we've drawn all the forces here, and they're asking us to find the reaction at plank C. So in order to find the reaction at plank C, what we're going to do is taking moments, okay? So I'm going to take moments, but as you can see, there are 2 different pivot points. So there's 2 different points I can take the moments about. A general rule, a tip is if I want to find the reaction at C, I take the moments at the other pivot. So in this case, I'm going to take moments about A, okay? So A is going to be my pivot. The reason being is if I do moments about A, any forces at the pivot would disappear, because as you know, moment is force times distance. So if I was to do the moments of RA, it would be RA times the distance. Distance of RA to A, well, that's just 0, right? So the moment for the RA is actually going to be 0. So therefore, any forces acting at the pivot we don't have to consider when doing moments. That's like a general tip you guys should always be remembering. So moments about A, clockwise is positive. So we have this 15g, so 15g multiplied by the distance. Now, as it says in the middle, if the whole plank is 5 meters, then half of that would be 5 over 2. And it's going to act in a clockwise moment, so it's going to be positive. We also have this RC times the distance. Well, the distance, if this is 2 meters here, the distance will be 3. And this is going to act in an anti-clockwise motion, it's going to be negative like this. And importantly, it says that it's an equilibrium like this, so we can say that the moment will have to be equal to 0, which I can solve for RC, and RC we should get 25 over 2g like so. Right, if they haven't asked us to find RA, right? But if they asked us to find RA, then I would have to do moments about C like this, the same equation where C is now the pivot, and do moments and make that equal to 0. But another, or an easier way or tip of I can actually do it as well. We know that the result, if it's an equilibrium, the resultant moment is 0, but also the resultant force is going to be 0. So I can now consider the resultant force rather than doing this moment equation here. So I can now resolve vertically upwards and look at all the forces acting in a vertical motion. Well, we have RA acting upwards, we have RC acting upwards, and we have the 15g acting downwards, so it's going to be negative 15g, and because it's an equilibrium, I can equal to 0. And because I found this RC here, I can plug it into here and then find my RA using this resultant force equation rather than the moment equation. So either both equations will give you the same answer, it's just that the resultant force equation is just a bit more easy and simpler and quicker to use. Anyway, carrying on the question, so we have a person of mass 45 kilograms stand at a plank at the point D, and it remains in equilibrium. The reactions on the plank A and C are now equal. Find the distance D. So let's just say he acts, maybe the weight is going to be 45 G like here, and they're asking us to find this distance as labeled at like X. Now importantly, what they told us is now the reactions at A and C are the same, so that means that RA is equal to RC like this. And so what I can do is work out RA and RC straight away. So the reason being is I'm going to resolve vertically upwards like before. So if RA acting upwards, RC acting upwards, the minus 15G of the weight acting downwards, but also there's also the mass of the weight of the man acting downwards as well, so it's minus 45G as well, is equal to 0. So RA plus RC is equal to 60G. RA is equal to RC, so I can say it's 2RC is equal to 60G. So therefore RC is equal to 30G, which also makes that RA is equal to 30G. So we know the reactions at each force. This will come in handy later on. Now, we're going to now have to do moments. So I'm going to do moments about A, okay? So moments about A. So remember we have the 15G here times the distance. So 15G times the distance, which is 5/2, minus RC times the distance, which is 3, plus this 45G times the distance we're trying to find X, like so. Now this is where what we worked out earlier comes in handy, right? Because we worked out that RC is 30G, which I can plug into this equation here. And now we only have one unknown like before, which I can rearrange or find, and X will give you 7/6 meters like so. So that's how we're going to use what additional information that they're giving us that the two reaction forces are the same to find this answer. Right, let's try another question here. So we have a uniform rod AB of length 4 meters and weight 20 newtons. And it's suspended horizontally by two vertical strings attached at A and B. So always draw it just to visualize them. So we have A and B. Now rather than supports, we're actually connected by strings. So the strings acting upwards. And if there's strings, rather than reaction, what we call them is tension. So we're going to call them TA and TB, like so. It's a uniform rod of 4 meters. So this length is 4 meters like this. And remember, uniform means that the mass acts in the middle, or the weight acts in the middle. And the weight is 20 newtons. So be careful of that. They haven't given us the mass, they're given us the weight. So the weight in the middle is going to be 20 newtons like this, not 20G. Just be careful of that. Right. A particle of weight 10 newtons is attached to a rod at point C, where AC is 1.5. So there's another 10 newtons added here, where this distance here, A to C, is 1.5 meters. Okay. To find the magnitude of the tensions in the two strings. So we're trying to find TA and TB. So the way we go about doing that is taking moments. So taking moments about A, going clockwise as positive, but the 10 newtons times the distance is 1.5 to A, plus the 20 newtons times the distance is 2 because it's in the middle, minus because TB is acting anti-clockwise, TB times the distance, which is 4 meters, and that's equal to 0 because it's in equilibrium. TB you get is equal to 55/4 newtons. Right, to find TA, I could take moments about B, but I can also resolve vertically upwards, right? This is a quicker way of doing it. So resolving vertically upwards, we get TA acting upwards plus TB acting upwards. We get minus 10 acting downwards and minus 20 acting downwards is equal to 0 because it's in equilibrium. Replacing the TB, which we found earlier, and TA, we should get 65/4 newtons. So that's how we go about finding the two tensions. Right, the particles move so that the rod remains in horizontal equilibrium with the tensions in the string at B 1.5 times the tension in the string at A. So they've moved this weight, and now what they've said is that the weight tension in TB is actually 1.5 times TA. So this is an additional piece of information that is very essential for us because we're going to use it later. Find the new distance of the particle A. So this is no longer going to be 1.5 meters. Let's call this distance X again. We're trying to find this X. But either way, it's still doing a moment. So moments about A again. So moments about A. So we have this 10 newtons, which is the distance of X, which we don't know, plus the weight, which is still in the middle, 20 times 2 in the middle, and then the TB times the 4 distance, and this is equal to 0. As you can see here, we have two unknowns. So we have this we have this TB and we have this X distance here. But luckily we found this, we're given this condition here. So what I can do is resolve vertically upwards. It's going to be the same equation as this one here, right? So TA plus TB is equal to 30 newtons. Now we're trying to find TB, right? So I need to replace TA. So you can see that TB is equal to 3 over 2 TA, so therefore TA is equal to 2 over 3 TB, which I can substitute into here. And that way this will give me the TB value. So TB, if I were to find it, will give me 18 newtons. And if I was to replace this TB into here, and then solve this equation which we got earlier, we get an X value of 3.2 meters. It's a very similar question to the previous one. It's just now we're using tensions rather than reactions. And let's do one final one. So this is now no longer in a pivot. It's now supported against the wall. So we have a uniform ladder AB leaning against a smooth vertical wall on a rough horizontal ground at an angle of 70 degrees to the horizontal. The ladder has a length of 8 meters and is held in equilibrium by a frictional force of 60 newtons acting horizontally at B. So let's just draw this out a bit bigger. So we have a wall, we have a ladder like this, and then now we have its weight in the middle. This is still a uniform ladder, and the weight of the ladder is something we don't know, so it's mg, we'll call it. With this force of frictional force 60 newtons like this, and it's A and B. So A and B are going to be the pivots. Now additional forces, because it's leaning against the wall, there's actually reaction forces going like here, so RA is like this, and then a reaction force going upwards, RB, like so. So this will be the force diagram for this kind of question. Write down the magnitude of the normal reaction of the force at A. So they're asking us for what RA is going to be. Luckily for us, what we can do is resolve, because it's an equilibrium, we can resolve forces. I can resolve horizontally, looking at the forces are in horizontally. Well, we have RA horizontally, and we also have minus 60 acting horizontally. These are the only two forces acting horizontally. So RA is going to be equal to 60 newtons, like so. B, find the mass of the ladder. So mass of the ladder, we're going to have to now resolve vertically. So resolving vertically, we have minus mg, because mg is acting downwards, and we have this plus rb acting upwards like this. And so we can say that rb, because is equal to 0, is equal to mg. However, these are both unknown, so we're going to have to find one of these. So what I'm going to do now is taking moments. So as I said, there's 2 points I can take moments about. I can take moments about A, or I can take moments about B. Now, as I said before, if you take moments about a certain pivot, all the forces at that pivot will disappear. So what I can do now is I'm going to take moments about B, because RB acts at that pivot B, and we don't know RB. So if I was to take moments about B, then the RB force will disappear, and I don't have to consider it. So moments about B, this distance here was 8 meters, remember? And so as you can see, it's force times distance, or the perpendicular force times distance. You can see that this angle they're giving us is 70 degrees, which is very important because the forces and the distances are no longer the same, or no longer perpendicular to each other. So if I was to consider this mg, the distance itself, if it's uniform, is 4 meters, but the force I'll need to find is this force here, not this mg. So the force is going to be 4 times that force component. Luckily, this angle here is the same angle as the 70, so 70 degrees. And so therefore, this component of that force is going to be mg cos 70, like so. And this is going to be acting in an anti-clockwise direction, so it's actually going to be a negative value, like so. Now, the other force I'm going to have is this RA. So RA, once again, the distance is 8, and I just have to find this component of that force. Luckily for us, this is going to be 60 degrees, so this is now going to be 60 degrees as well, meaning this is going to be 30 degrees, like so. So this is all about looking at angles, and that component is going to be 8 times RA cos 30, like here, and that's going to be acting in a positive direction. It's going to be plus, and that's all going to be equal to 0. And then I can rearrange to find my mg, because I've found my RA from earlier, which was 60 degrees, which I can plug into here, and then rearrange to find mg. This is a slightly more difficult question, but the same concepts apply. The force and the distance have to be perpendicular to each other, and you can be given some angles in order to find the correct component of that force.